So we're going to start getting into our shapes and start diving into different shapes, and we'll start with triangles. Um, and eventually talk about everything there is to know about triangles. We'll eventually talk about how to prove two triangles are congruent. So chapter 4 is going to be pretty heavy into some proof writing as well. So all those proofs are going to start coming back at you quite a bit. Okay, so, but today, the first two sections are a lot of review, a couple of things that might be new ideas for you, but nothing too strenuous, I don't think. So we'll start by talking about triangle sum properties and how to classify triangles. Okay, first definitions. Triangle is a polygon with three sides. Remember, a polygon is just any geometric figure that's made up of three or more segments that we call sides, obviously, and the sides need to meet at endpoints so that they form a vertex. A triangle has three sides and therefore has three vertices, plural of vertex. That's just each of the corners of a triangle. A triangle has three corners, obviously. And then if I had asked you before we started this, the three angles of a triangle, what they add up to, my guess is most of you would probably remember that they add up to 180 degrees. Okay, these are all things you need to remember, especially the definition of a triangle. Remember that vocabulary is definitely a part of your test, so make sure that you're studying all of that stuff. Okay, but I think you guys know what a triangle is. Now, triangles we can type. We typically type triangles based on side lengths, and then we also type them based off angles. In your notes, these are all sort of thrown together. It might be helpful if you create a couple of sections here. And so the first three definitions that you're looking at are how we classify triangles by their sides. And so what we look at is, are any of the sides congruent? And if all three sides are congruent, that means we have an equilateral triangle. And so if it's an equilateral triangle, then we would know that it was an equilateral triangle by showing that all three sides were congruent to each other. And we use these tick marks to show that. Remember, tick marks is what we use to show that segments are congruent. We use arcs to show that angles are congruent. We'll get back to that in just a little bit. So three congruent sides, equilateral triangle. We reduce that down to two congruent sides, and we're talking about an isosceles triangle. It would look something like this. So again, two of the sides are congruent, the third one is not. And then a scalene triangle has no congruent sides. And so we wouldn't be able to put tick marks on any of the sides if it were a scalene triangle. Now, one thing I do want to point out is that in an isosceles triangle, the definition is that it has at least two congruent sides. And so what you'll see happen sometimes is that if a triangle has three congruent sides, then it is an equilateral triangle, but it's also considered an isosceles triangle because it does have at least at least two congruent sides. So an equilateral triangle is also considered isosceles for that reason. Okay. Now, moving on. So that's how we classify by sides. And so you might want to draw a line in between scalene and acute triangle and make a side note someplace that says this is how we classify by the sides, because then we're going to classify by angles. And when we classify by angles, it's all about what types of angles are inside your triangle. First type of angle we have is an acute angle. And so if a triangle is made up of three acute angles, then we call it an acute triangle, of course. Okay, and so it might be something like this, where your three angles are 45, 55, and 80 degrees. Now, it doesn't have to be 45, 55, and 80. It can be any combination of angle measures. As long as they're all acute angles, then it's an acute triangle. We also have right angles, and so it's possible for a triangle to have a right angle in it, one right angle, in which we call that a right triangle. Can only have one right angle in it because If you have two right angles in a triangle, you add those two 90 degrees up, you get 180 already, and you have to have a third angle to add in there, and the angle measures can't add up to more than 180 degrees. So right triangle only has one right angle in it. And then we'll stop for a second. And in a right triangle, we also tend to name some of the sides. So a little bit more information about right triangles. The two perpendicular sides, the two sides around the right angle, are called legs. Okay? They're the two sides that are perpendicular, that are attached to the right angle. The side that's across from the right angle is called the hypotenuse. Hypotenuse is always the longest side, and it's always across from the right angle. And being able to pick out the hypotenuse in a right triangle is going to be really important to us later. So make sure that you are aware and remember where the hypotenuse is. Okay. Now, while we're talking about names of sides for triangles, I'll go ahead and throw in the names of sides of an isosceles triangle. So go back up to isosceles triangle, and in an isosceles triangle, we name sides as well. The two sides that are congruent are called legs. So isosceles triangles have legs just like right triangles do. And the third side is called the base. Okay? Now, since that third side is called the base, we also do have specific names for these angles inside the triangle that are next to the base. So angle 1, angle 2, these guys are called base angles, cleverly called base angles because they're next to the base. Okay? The third angle actually has a name as well, and so this third angle we call the vertex angle, which is not quite so obviously named. Get a lag here in my dossary, but the vertex angle. Okay, the vertex angle is always in between the two congruent sides. Okay, the base angles are always the angles next to the base, but we'll have some theorems that talk about the base angles and the vertex angles, and so we want to make sure we can pick those out in an isosceles triangle as well. Okay. Right triangle has a hypotenuse and two legs. Remember how to pick those out. Okay. Now, back to classifying the triangles. So we have acute angles, we have right angles, we also have obtuse angles, and it's possible for a triangle to have one obtuse angle in it, and if it does, then that we call that an obtuse triangle. Can only have one obtuse angle in it because, again, the angles have to add up to 180. Obtuse angles are bigger than 90. If you have two in there, then when you add two angles that are bigger than 90 together, you get more than 180. And so that's too much with a third angle still left to add in there. So only one obtuse angle, only one right triangle. Only one obtuse angle in an obtuse triangle, and only one right angle in a right triangle. Okay? So that's how we're going to classify them. And you'd have to know, so just like in our sides, you'd have to know which sides were congruent, if any, to try to classify by sides. And angles the same way. You'd have to know angle measures in order to try to classify a triangle by its angle measures. Okay? Now, if we have a triangle that we want to classify, but we don't have the side lengths, we can take that triangle and put it into a coordinate plane. And when we put that triangle in a coordinate plane, it creates coordinates for our vertices. And so if I wanted to classify this triangle by its side lengths, then we'd have to go find the side lengths and see if any of them are the same. So in other words, I'd have to go find the length of this side, and then the length of this side, and then the length of this side. You have to remember, how do you find the length of a side? A side is a segment. How do you find the length of a segment if it's in the coordinate plane? And the length of a segment is the same thing as the distance from, say, point P to point Q. So if I want to find the length of PQ, I have to find the distance from point P to point Q, which means I have to use the distance formula. Distance formula is subtract the x's and square them. Subtract the y's and square them, and then square root them. So if we were to plug in the coordinates here, the x's for p and q are 6 and negative 1. So we get negative 1 minus 6. And the y's are 2 and 3. So try to get this in here. So negative 1 minus 6 is negative 7. Negative 7 squared is 49. 2 minus 3 is negative 1. Negative 1 squared is 1. And so we get the square root of 50. Now we've got to do the same thing for the other two sides. So for OQ, or QO, however you want to name it, subtract the x's. The x's are 6 and 0, and then square them. Subtract the y's. The y's are 3 and 0, and then square them. And so 6 minus 0 is 6. 6 squared is 36. 3 minus 0 is 3. 3 squared is 9. So we get the square root of 45. And then we got to do the same thing for PO. Subtract the x's. The x's are negative 1 and 0. Subtract the y's. The y's are 2 and 0. Negative 1 minus 0 is negative 1. Negative 1 squared is 1. 2 minus 0 is 2. 2 squared is 4. So we get the square root of 5. Okay? Now, are any of these sides the same? Well, obviously not. So that means this must be a scalene triangle. Okay? Now, can you classify it by its angle measures, by its angles? About the best thing you could do is try to determine if there's a right angle in this triangle. And we can do that since it's in the coordinate plane. A right angle is formed by two lines that are perpendicular. So we could find the slopes of all three of your sides and see if any of those are those opposite reciprocal slopes to make those sides perpendicular. That's about the best thing we can do. That being said, we'll leave it at just trying to classify by its side lengths and not worry about the angles right now. Okay? All right. Now, some theorems that involve the angle measures of a triangle. And so before we get to that, we have postulates and theorems as rules in geometry. Postulates do not need proofs. We just accept them as being true. Theorems we do have to prove before we can accept them as being true and then go use them. Corollaries are kind of like amendments to theorems. They're extensions to theorems. And so what we mean by that is corollaries are sort of tied to a theorem. They just extend the theorem to a special or specific situation. And you should be able to use that theorem to prove the corollary. So again, it's a rule that would need a proof in order for us to accept them as being true, and then be able to use it in anything going forward. Okay? So the first theorem we have is called the triangle sum theorem, and it's what we've already talked about. The triangle sum theorem is just a theorem that tells us that if you add the three interior angles together, you're going to get 180 degrees. Okay? Oh, we missed a slide here. So before we get to this, let's back up for a second. Okay? Let me get through this. Let's back up a second. Skip the slide. Sorry. We'll come back to those angle theorems in just a second. We need to talk about exterior and interior angles before we get to those theorems, and so we'll go back. First of all, interior angles. Interior means inside. Inside, the angles are the angles that you've always looked at, always talked about. It's the original angles. You see them over here. And so angle 1, angle 2, and angle 3 are all going to be your interior angles. Okay? So these are all your interior angles. Exterior angles are formed when we extend the side of a triangle, right? We've talked about before the fact that segments are just parts of lines. And so since the sides of a polygon are just line segments, there really is a line that exists through that segment. So we have the option of extending a side. When we do, we create what are called exterior angles. So if we extend this side out this way, then we create this exterior angle right here. Okay, angle 7. All right, and so there's some things we know about exterior angles. Okay, so some things about exterior angles. Exterior angles form linear pairs with the interior angles. So angle 7 and angle 1 form this straight line. They're a linear pair. Okay, but all the exterior angles form a linear pair with an interior angle somewhere. So if we were to extend this side, we'd create this angle, angle 4, and angle 4 and angle 1 would be a linear pair, 3 and 5, 3 and 8 are linear pairs. So you just have linear pairs all over the place here. And linear pairs, remember, have to add up to 180. They're supplementary. So, while we're talking about it, we also have some vertical angles in here. So don't forget that. This guy and this guy are vertical angles. Right? And so are 7 and 4, so on and so forth. So when we extend those sides, we get those angle relationships that we've talked about before. Okay, so the exterior angles, interior angles. Now it makes sense to go back and talk about these theorems. Okay, so the triangle sum theorem, the measures of the interior angles add up to 180. Okay, there is. We can also talk a little bit about exterior angles. So we have these two, this exterior angle down here, angle 4, which is a linear pair with angle 3. We just saw that in the definition of an exterior angle. So what does that mean? That means that the measure of angle 3, make that better, plus the measure of angle 4 is equal to 180, right? We'll take a look at the triangle sum theorem here and what we just did with the linear pair here. I've got two things that are both equal to 180, two different things. So I can combine those. The measure of angle 1 plus the measure of angle 2 plus the measure of angle 3, since it's equal to 180, and since 3 plus 4 down here is equal to 180, then I can set those two equal to each other by using transitive or substitution, whichever one you like. Okay? Now, from that idea, I see that I have the measure of angle 3 on this side and the measure of angle 3 on this side. So I can actually subtract those out from this equation. And I'm left with the measure of angle 1 plus the measure of angle 2 has to equal the measure of angle 4. In other words, these two guys added together have to be equal to that guy. And that guy, angle 4, is an exterior angle. So this gets us to our exterior angle theorem. Okay, and I just proved it. And the exterior angle theorem says exactly what I just showed you. It says that the measure of the exterior angle is equal to the sum of the measures of the two non-adjacent or the two away interior angles. Okay, and so to see that in equation form is here. The measure of angle 1 plus the measure of angle 2 has to be equal to the measure of angle 4. All right, so exterior angle is equal to adding up the other two interior angles. It's a very different theorem. You may not have seen that before, but something that can be very useful for us later on. Now, the next theorem, next rule we're going to take a look at, it's not a theorem, it's a corollary. It's an extension from the triangle sum theorem, right? So this guy up here, what if angle 3 was a right angle? If angle 3 up here was a right angle, then we would know that the measure of angle 3 was 90 degrees. It would always be 90 degrees. So if we subtract 90 from both sides in this equation, then what we'd be left with is the measure of angle 1 plus the measure of angle 2 equals 90 degrees. Well, if angle 1 and angle 2 add to 90, then by definition, angle 1 and angle 2 are complementary. They're complementary angles. So what this corollary says is exactly that. Angle 1 and angle 2 would be the two acute angles of a right triangle. And so we know that the acute angles of a right triangle must be complementary because of what I just showed you. Okay? So we can use this corollary to help us show that that angle 1 and angle 2 here are complementary. And can also use it to just, if I need to find angle 1 and I know angle 2, I can just subtract angle 2 from 90 and find out what angle 1 is. So it can kind of shorten our work for us a little bit too. Okay? So some theorems and corollaries you need to be familiar with and you know how to use. And one use of that could be something like this. If I have a diagram like this and I want to find the measure of angle JKM. Well, the measure of angle JKM. Well, angle JKM is here. It's an exterior angle. And if you go back to your theorems, there's the exterior angle theorem, which says that the exterior angle is equal to adding up the two angles that are away from it. So what we want to do here is take 2x minus 5. This thing is lagging. And set it equal to x plus 70. And then go solve. So subtract x, and we get x. Add 5, and so x is 75. Now, we found x. It didn't ask us to find x. It asked us to find the angle, the measure of angle JKM. So we'd have to go plug in x here. So 2 times 75 minus 50 gets you to 145. Okay? Which means, oh, by the way, if that angle is 145 degrees, that means this angle has to be what? Well, it has to be 180 minus 145. Which is 35. Okay, don't forget, those guys are supplementary. They're a linear pair. Okay? So a use of that exterior angle theorem. All right, that's our angles. That's our angle theorems. And how do we classify triangles? Now let's talk about triangles being congruent. Okay? What does it mean for triangles to be congruent? Well, first of all, for any two figures are congruent figures if all the parts of one figure are congruent to all the parts of corresponding. So parts of one figure are congruent to the corresponding parts of the other figure. And so in polygons, this means that the corresponding sides must be congruent and the corresponding angles must be congruent. And this corresponding is pretty important. Okay, that means that parts match up. Angles and sides are going to match up, and we have to be really careful on how we write things and how we approach things since there is this correspondence. Okay? So, some quick notation. If two figures are going to be congruent, if two triangles are going to be congruent, then we would need to know that all the corresponding parts are congruent. In other words, we would need to know that a side in this triangle is congruent to a side in this triangle, so maybe AB and EF. We would have to know that BC and DE were congruent. We would have to know that AC and DF were congruent. And the way we show segments congruent are those tick marks, or what this is called dash marks. But tick marks on the sides, on all the sides, will let us know which sides were congruent. And there's your correspondence. AB corresponds to EF. AC corresponds to DF, and these two guys correspond. Okay? Same thing with angles. The angles would have to be congruent to each other, and there would be a correspondence. Here, angle C and D are congruent. Angle B and E are congruent. And angle A and angle F are congruent. And so those are your corresponding parts. So what we could do is write what we call congruence statements, which we'll talk about and see in just a second. We know that from these two diagrams that segment AB or side AB is congruent to its corresponding side EF. Ugh, this thing is sticking. And that side AC is congruent to side, DF. And we can go all the way around. Same thing with angles. We know that angle A is congruent to angle, F. And so on and so forth, down our angles, okay? Now, this doesn't make much sense to me, but when you're naming triangles, we need to be careful on how we name triangles, and we'll talk about that in the next slide here. So congruence statements. All these things that I just wrote over here were called congruence statements. This is a statement that tells us what parts are congruent, or what things are congruent. This is congruent to that. When we write congruent statements, and the ones that we've written so far were only, things like this segment's congruent to this segment, this angle is congruent to this angle, and so we haven't really had to worry about matching things up. But when you write a congruent statement, you have to make sure that the corresponding parts match up. You have to make sure that in two triangles, the corresponding angles and sides match up. Now, how do you name a triangle? Naming a triangle is pretty easy. We just start with the vertex and we work our way around, either clockwise or counterclockwise. So this first triangle, ABC, could be how we name that. So we go counterclockwise and call it a triangle ABC. Now there is a symbol. There's a little triangle that we put in front of the ABC to let us know that we're talking about a triangle. So in our congruence statement between these two triangles, which are congruent triangles, we have some different options down here. If we call the first one triangle ABC, then we have to make sure that the second triangle, when we name it, we list the corresponding parts together, that they match. In other words, in this particular diagram, angle A and angle D are congruent. So if I list A first in the name of triangle ABC, then I have to list D first in the name of triangle D in the second triangle. And then B came next, and so B corresponds to F, so that means F has to come next here. And then C corresponds to E, and so E would have to come last. So the idea behind this is if you didn't have the picture to know which parts were congruent, you should be able to tell by the name. And so the name here tells you that angle A and angle D are congruent, B and F, C and E are congruent. It also tells you that side AB and side DF are congruent, and that side BC and side FE are congruent, and that side AC and side DE are congruent. And so it matches them up with their names. And if we decide to we can name our triangles whatever we want. As long as our congruent statement matches up our corresponding parts, we're fine. So name triangle ABC in some other way. Maybe CAB. If we go CAB, then C is supposed to match with E, so that means we have to go E first here. Then A matches up with D, so D comes next, and then B matches up with F, so it would be EDF. And so on and so forth. BCA is another way we can name that triangle, which means that this triangle would have to be called FED. Okay? Match them up. You have to match them up. Okay? All right. Now, another theorem for you called the third angles theorem. Makes a ton of sense. If we've got two triangles and two angles of one triangle are congruent to two angles of another. In other words, if we have this situation going on in the diagram, then hopefully quite obviously, the third angles are going to automatically be congruent. That's the third angles theorem. If two angles of one triangle are congruent to two angles of another, then the third angles have to be congruent too. Okay, without measuring or any other information, we automatically know that's going to be true. All right. So the use of that. Okay, in this next example, we want to find the measure of angle BDC. And right now in this diagram, we know part of angle BDC, but we don't know the whole angle BDC. How can we go find it? Well, actually there's 5 triangles in this diagram, right? And here's 2 of them. Here's one, and here's one. So we've got 2 triangles that are overlapping. Anytime that happens, I think it becomes very useful to redraw these triangles so that they're separated. And once you redraw the triangle, you want to name it the same way it is in the picture. So this is ACD, and this is CBD. Now, angle A has 1 arc in it. I want to make sure I put that arc in there. Angle B over here has 1 arc in it, so I want to make sure I put that arc there. Angle D down here in the first triangle has 2 arcs in it, so I want to make sure I put that in there. And angle C in the other triangle has 2 arcs in it. I want to make sure I put that there. I also have some angle measures. Angle A is 45 degrees. Angle D in this same angle, or the same triangle, is 30. And so that's all I know. Now, what this diagram tells me is that these angles are congruent and these angles are congruent, which means that automatically these angles are congruent. So if I find this angle, then I'll be able to find this angle. Okay? Well, we find angle C by remembering that if you add up the angles of a triangle, they have to add to 180. Right? So this is 75. Subtract 75 from both sides and you get 105. So this angle is 105. Now by the third angle theorem, D over here has to be the same thing. So angle D is going to be 105. So the measure of angle, BDC has to be 105 degrees. Okay? And you could also use the fact that that these guys are congruent, and so the angle B is going to be 45, and this angle is going to be 30, and now use your triangles, or the angles have to add up to 180 to get it. There's a couple different ways you can approach it, but this is definitely one. Okay, using that third angle theorem. Okay? All right, got one more thing to talk about here. We've got some properties, and then we're going to take a look at a proof. And these properties are familiar properties as well. The reflexive property, all this is showing you is that all these properties that we saw before are that can follow with triangles as well. So the reflexive property, which says that something is congruent to itself, right? It just means that triangle ABC is congruent to triangle ABC. The next property is the symmetric property, which says that if I know